Okay, I think we're ready. So this talk is going to be by the wonderful Rick Waldron.
Hello. Thanks. Is this thing on? Is it on?
Is it on yet? Is this mic on? Good.
Cool.
Okay.
Oh, there we go.
Awesome. And he is going to talk about robots, and specifically teaching them to walk. This is really neat.
Good afternoon. I'm Rick Waldron. I work at Boku. You can follow me on Twitter there if you're interested in hearing me rant and rave about garbage or robots. A lot of garbage, a lot of robots. Follow me on GitHub without vowels. It was a phase. Not sure how to explain that. So about 7 months ago, I started working on this sort of research and development project at Boku during my open source time called Johnny 5. Johnny 5's goals are to be a framework for programming microcontrollers, specifically in most common cases Arduinos. Supports a number of different Arduino boards and releases, so everything is very, very, very much constantly in development and no guarantees, but it's fun. And basically, one thing I need to remind everybody about, and I always touch on this because you have to have a fundamental understanding that hardware is intrinsically synchronous. So hardware exists in real life, right? This thing exists in real life. It's a thing. Everything that you do with hardware actually takes time. Chronologically, it takes time. It's very temporal. So you have to think, when I want a piece of hardware to do something, I tell it to do that, and I have to wait till it's done before I can tell it to do the next thing. So keep that in mind as we move forward. It's an important thing. It's an important concept to grasp onto. It's not something that you really think about very much when you're writing software necessarily, especially JavaScript, which is asynchronous. Real quick though, so at past talks that I've given, specifically at NodeConf in Portland, I talked about how synchronous input needs to be handled asynchronously, right? Especially when we're writing programs with JavaScript and in Node. So we have sensors, right? You saw what Emily had earlier, and even in the kegerator, there are sensors. They're reading in the environment. They're doing something. They're programmed ahead of time at a factory to read some aspect of the environment. Maybe that's a temperature, or a light sensor, or flexi bend sensor, or something that I touch and it reads back how much pressure is on it. So think about, this is just a constant flow of information, right? So it reads back, it sends it to the microcontroller, and the microcontroller then sends it down the serial port, which receives it, turns it into streams, and then we wrap events around it. When we know what the piece of information looks like, when we get something that we can reason about, we turn it into an event, as in bend, or touched, or if it's a button, pressed, or the temperature of the kegerator has dropped below, whatever. So just to give you an illustration of that, I'm going to refer to myself back at NodeConf to demonstrate for you a few small concepts of reading with sensors my environment and reacting accordingly. So this is not funny. Stupid me. There we go. So here's what's happening. You remember these ultrasonic sensors that Emily was showing? They're reading in the distance between itself and this physical object in the real world, sending information. Look at what the... Hey. All right, so as you can see now, for those of you that can see, this robot was actually able to figure out its way out from between those two garbage bins. It was great. It was right on stage. Everybody got to witness it. And what it did was it read its environment. It said, what is physically in front of me, right? Physically in front of me, constantly coming in. And now change the way the servos are directing, like change the speed of the right to lower it down so that the left will force it to turn, or otherwise turn this way. But we constantly need to be able to read in, right, asynchronously without ever blocking this program. So this is actually going to be really important to where we're going with this. I actually haven't even gotten to the beginning of the show yet. This is all just like previously on Lost section, right? So, is everybody with me? You got that? Pacific Northwest reference? Teaching nobots how to walk. So we talked about asynchronous input, and hopefully you all have an idea of what I'm talking about with asynchronous input. What about asynchronous output? What about when I want to tell something to do something at a certain time, perhaps now or perhaps later, or what do we do in between? So basically, I want to do task A to completion before we start task B. Okay? Who, in your mind, you start thinking like, oh, I know what I would do. I got some ideas about how I might do that, right? Probably not good ideas, but we'll get to that in a second. I want to underscore some fundamental principles here. Sequences. These are tasks, that one following the other, right? So you can always say, I have a task, 1, 2, 3, and I want each one to complete in order. This is a sequence of tasks. Easy, we all know this stuff. So if we consider perhaps changing the position of a servo horn, right? If we want to start at 90 degrees, right? This is 90 degrees. Right? As you can see, I've illustrated it right here. Great, awesome. So we want to start at 90 degrees. We want to move the position to 135 degrees. As it turns out, this particular servo will take 346 milliseconds to reach 135 degrees, right? It's not very long. It's actually really fast. But it does take time because it's synchronous, because it exists in the real world. It's a physical object that has to move, right? Then we're going to move it to 0 degrees. That actually takes a really long time because it's got to go all the way back, right? Then to 45 degrees, which then again takes more time, and then to 180 degrees, then back to 90. Now, if I were to just call functions that wrote these values to the servo, one right after the other, right? What would happen was we would jump from 90, probably back to 90, and you wouldn't see anything happen. Because it would say call, 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 right? But then it would say, oh, well, the most recent information I have is to just stay where the hell I am. You might actually just see a little tick. But if we actually want to see these things happen, each step actually illustrate before our eyes, we need to say only commit to the next task once this certain amount of time has gone by. Oh, my apologies. I should show you that, the video. So it'll look something like this. Right? This makes sense. Does this follow now? Everybody shaking your, come on, wake up. I know you're thinking about Skyfall and beer now. Thanks, everybody. So traditionally, in hardware programming, the concept of delay to, it's on an event loop. Hardware generally exists, its programming model is a loop, just constantly executing this one piece of code over and over again. So now, if I want to have a series of sequenced tasks, we might do something where we execute, then we delay until that's done doing the task that it wants to do, which is actually stopping the execution of the program for however many milliseconds we tell it to, or perhaps microseconds, depending upon what systems you're working on and what your capabilities are. But it doesn't matter. It's still blocking execution. And this is something that you can't do in node.js. Fundamentally, you can't block because it's a single thread. Now, remember back when I was talking about sensors, asynchronous input. Could you imagine what would happen if we took away our ability to see, right? Well, I'm a human, and I'm pretty good at figuring out that I fell off, right? If I was a robot, I would have no idea. So imagine we block execution, but the servos are still moving forward. But we're not getting input. So you could see how this can become devastating to the program that's running. So imagine a world where to actually be able to move the servo horn as we had, right, in the demonstration in the video previously, just attach a servo to this pin. We're talking about Arduinos here, right? Write the position, delay, write the position, delay, write the position, delay, so on and so forth. This adds up to about 4 seconds of blocking, all told, which is, I mean, how many people here think that might be good for their programs? I'm pretty sure no one's going to say yes. We could do that with JavaScript, right? We could do like a blocking while loop for a certain amount of time. I'm not sure I would want to commit to that, though. So, did somebody just say you have no idea? It's Bob, Twin Peaks. Come on. This is all my jokes. All my jokes are from Twin Peaks this time. So real quick, let's just get like a firm understanding of blocking execution. Who here thinks they know what blocking execution does and can actually demonstrate it? Right? No? Wow, really? Do you know what an alert is? Do you know what happens when I can't do anything? Imagine I'm a sensor. Just stretch your imagination for a moment. I'm a sensor trying to tell a program what's going on. Oh my God, we're going to fall off the edge of the stage and embarrass ourselves in front of everybody. Your grandmother's going to watch this video later. Can't do it. Until we unblock. So, how many of you earlier thought like, oh, just use set timeout? Raise your hands. Just be honest. It's cool because that's what I did first too. Unfortunately, it looks like that eventually. And what happens when I have like an arbitrary number of tasks that I want? Like this is not composable, right? I even have a slide that says, no thanks, it's not composable. It doesn't scale. You end up with, not only do you end up with like visual drift, you end up with time drift as well. You end up with these bizarre disparities of like how long did this actually take to happen, and it's unreliable and it's just ridiculous. Node itself has a built-in concept of it has the timer bindings, right? The timer wrap. It gets close, but that's all that set timeout actually does. I mean, you could write your own abstraction on top of that, but you'd still suffer those same time disparities that set timeouts would suffer, even no matter how you develop your own API around that. So I'm going to skip that altogether, right? Because my log has something to tell you. Here today. Process next tick. Who here is familiar with process next tick? Yar. Yar? Right? Everybody is familiar? No, nobody is familiar at all. Come on. Seriously? You guys are like, no, just show us the robot. I'll show it to you in a second. I promise. So basically, with process next tick, you schedule a callback to happen in the next execution turn. So what happens if you just keep calling process next tick in a loop, right? Keeps going, keeps going. Now, what if you had some sort of minimal computation also within that loop? Say, a list of temporal tasks, perhaps a set of delays or loops, basically a queue of tasks, if you will, that just for giggles might look something similar to this. Now imagine each one of these is a key that represents a time in reality, right? To demonstrate, hopefully this makes sense. Execution happened, but the process kept going. We didn't stop the process, right? Because stopping the process might look a little bit like, wait for it. Oh, that's a friggin' bummer. The program obviously has stopped to execute those tasks, but then it's going to continue going, right? So you can imagine now if I have this minimal computation that I allow myself, say, writing to a serial port in this time frame, we could think about creating a registry of sequences that allow us to do such things that make it appear as though we have control over like the temporal landscape of our Node.js program. For example, you might want to animate across an LCD screen. Each one of these is just a fragment in time that says move to the cursor to the next position and write this little glyph, okay? That's all this is. It's just a loop, right? Just a loop. And each time one of the tasks executes, it says, am I a repeating task? I am, great. What time is it right now? Add my looping time to that time, schedule me to happen again in the future. And when it's done, if it has like a stopping point, it's simply don't continue, right? And at this point, we're never blocking, okay? We're allowing the program to continue as normal. We're just saying, hey, also, we might have some things scheduled that we have to run. We have an itinerary, or not. We may not always have a task to do. Oh, that's so. This is a sort of like when I spoke at Empire.js about a similar thing. Everybody got really excited about this, and I'll show you in a second just how excited they got. But what I want to demonstrate here is a simple repeating task as well, to give you an idea of this looping thing. What this is going to do is just two servos that are attached to each other with a wire tie, and they're facing in two different directions, which means that if we give them both, if we write the same value to both of them, you're actually going to see some sort of opposing behavior. So it just looks interesting. And all it's going to do is move the arms, right, like this. But it takes time, right, to get from one point to the other point. In fact, it takes 500 milliseconds approximately for it to make that entire movement. So when I showed this to the people at Empire.js, they got really, really excited. So excited that they all they were like, let us show you how it works. And I was lucky enough to capture that for forever and put it on the internet very shortly after my talk. I'm not going to make any of you do that. So traditionally, that program might have been written something like this, where we create two servo instances and we start at 90 degrees and we attach them in a setup phase, and then we have this loop where we just say, all right, where are we at? What is the current value? Update it to a new value and write the same value to those servos, and then stop for 480 milliseconds. Then it passes, and then we continue again and produce it. And that program is going to have this behavior that you just saw in both videos. If we were to program humans to do funny things at conferences, or just two servos that are attached together, you would see a similar behavior. Now, we could do the exact same thing without ever blocking the program by, this is a sort of a pseudo API. We have this temporal loop that says, schedule me to happen every 500 milliseconds. And it just executes and then moves on, executes and moves on. Instead of stopping and saying, all right, well, now you have to wait for me to update, to wait for those arms to get into the correct position, right? It doesn't do that. It just sends the information and says, all right, 500 milliseconds later, we're going to need to do this again, and so forth and so forth and so forth. So if we recall this example again, you can imagine that how we were able to move this around was pretty heinous, right? We're setting the servo position and then delaying. And it was awful, and Bob showed up and was part of our nightmares, and it was really, really, really awkward for everybody involved. So what if we were to have a queue of task objects where we defined a certain amount of time to delay and then a callback to execute in that amount of time? So you can imagine we begin to say, all right, well, in 346 milliseconds, but the second one also has to be cumulative and so forth, right? So you end up with a linear registry that looks a little bit like this. These are just a breakdown of the delay in the actual cumulative amount of time. So imagine that the queue was called at about that time. That was actually yesterday, so don't try to look it up right now because it'll come up as yesterday's date. Not magical. I wish I was. Maybe in the future I'll gain some magical powers, but not today. So imagine, if you will, process next tick loop from earlier, right? It gets to this time, and it says, we've got these tasks, so execute. It goes further, and then when it gets to 1 second, and then 382 milliseconds later, right? We're here, great, execute that, and so on and so forth. We could actually do that servo position change without ever blocking, without having those delay calls. What does all of this have to do with walking? Walking, this is the funny part where I make an ass of myself, just in case you were wondering. Walking is just a sequence of movements, right? Of singular units of movement. So you can imagine, like, as human beings, you break it down to a step, right? That's one step, and that's another step. So you can imagine it takes me actual time to do that, right? So now, let's apply that to a robot that has limited range of motion. It has two servos in its hips and two servos in its feet, right? Because that's about as far as and advanced as I can design just as of yet. So bear with me. You might do something like this to make it walk. Tilt to the side, swing around, and flatten. That's one step, right? Tilt to the other side, swing around, flatten, and that's another step. So we break it down into each step, and then you have, obviously, which position is which side that we're stepping on. And now, if we want to walk, we have to make a sequence of tasks, right? That have to happen on repeat. without ever blocking the program, because one day this is going to want to have eyes so that it can see where it's going, and we don't want to block that input. As of now, it will walk off the edge of the stage. I've decided to include this gentleman to help me illustrate how this looks when it walks. It's something similar to this. All right? You can see how he moves like this, right? All right. So, why don't we just get to the nitty-gritty? So, for those of you in the back that are going to not be able to really see what's going on here, I do have a video, which I'll play afterwards. But for those of you in the front, or if anybody wants to just fill in, you can feel free to. And hopefully this doesn't blow up in my face. So each step is just a task that's been queued in time, and then it says the next time around, which is about a second and a half, do the same task again. And it just keeps a piece of state internally that says which side is stepping at which point. And from there it just says, all right, let's loop this. And then it's a robot that walks across the stage. And then I tell it to back up, it'll do that as well. Unfortunately, on slippery surfaces, it has a tendency to turn, but which it did. So, I don't know about you, but when I learned how to walk, the next thing I learned how to do was dance, right? Right? One second. The robot would like to show you in person. Unfortunately, I don't have the music queued up. Oh. Oh, there we go. It was just break it down really well, right? So those are its dance moves that it learned, right? And that's all I got for you. Follow all of these people on Twitter. If you want to know more about robots and JavaScript, follow all these people. Go to that address and check it out later if you want. And I'm sorry that we will never know who killed Laura Palmer.